Okay, so the last topic was X-ray photoelectron spectroscopy. The reason we focus on, we can deal with a lot of aspect of XPS, but the reason for the last time was about the bio interface, which we have a surface and then serum protein as well, and then we analyze how to analyze such a thin layers of protein on the surfaces by the spectroscopy. So last time the XPS gives you about the chemical information of the protein or DNA or biomolecules on our surfaces. So today how to image on that the molecules are on the surfaces. So we talk about first atomic. So the AFM. So this is atomic force microscopy, as name indicated that this is a microscopy. So you can image the surface, how the roughness of the surfaces, and then or thickness of the surfaces, and then general morphology of the surfaces in which biomolecules absorb on it. So the thing is that you have a very flat surfaces now here. So the glass or silicon oxide, many different surfaces, which you want to culture the mammalian cells. And then remember, the mammalian cell has to require protein layers, to which the mammalian cells recognize protein and to which the cells are growing to. So now we can probably need a technique that how the molecules are absorbed on surfaces. So if we have, say, some microscopy, proteins are absorbed on it here, and then sometimes we need to image the patterns or morphology of the surfaces where the proteins that requires the cells then image this. So this technique we called atomic force microscopy can successfully image about the thickness of the layer down to 1 nanometer. Or sub-nanometer also possible, very easily can image this technique. So it's amazingly sensitive to in terms of the thickness of the surfaces. So we can now talk about the principle of how such a microscopy can image surfaces now. So before we going into details, maybe we can have some background of the history of this microscopy. So in more generally speaking, we can scanning force microscopy. That basically this technique requires very thin and very sharp. We call this cantilever. It's a cantilever that has very, very sharp needle, to which we say we have the surfaces looks like this, and then they actually can follow this morphology by scanning this sharp tip on top of the surfaces. Basically, how they operated this way. Okay, so this scanning probe microscopy SPM is the AFM is a subclass of the scanning probe microscopy, which in the previous was I mentioned scanning force microscopy was it's a wrong term. This scanning probe microscopy is the right term. So this AFM is the family of the scanning probe microscopy, which we have the contact mode. and this non-contact mode there's two modes exist in generally speaking. So this technique is basically, as I mentioned, is sharp tip, in which we have some object, which in this case is protein or DNA, that can follow this morphology of the surfaces. So you can imagine that if we operate this contact mode, then it's probably you can imagine this is one or two several nanometers, 2 3 nanometers of the protein, and then there should be a force exist that can actually push down to this protein, that the morphology of the protein can be distorted, so that actually you cannot see right and correct morphology of the surfaces if we can operate this contact mode because of the force. So the people now can use the non-contact mode, which is amazingly, this probe doesn't touch actually these surfaces, and they actually created the exact same morphology of the surfaces. It's amazingly that it's also counterintuitive to how the probe actually doesn't touch the object of surfaces, but how can they image? So now let's begin with explanations of how they how they operate it. So now this topic becomes atomic force microscopy, which non-contact mode we're talking about from now on. So probably we can think that these situations where in general physics, back to your several years ago, if there's a two object or two atoms here, and then these two atoms are distance you can control of these two atoms. So this is distance. The x is distance, and the y-axis is force. Okay. So this now the distance d between the two atoms are changed now. So generally speaking, if you have this as positive force and negative force, so negative force is attractive force. So this is attractive, and this is a repulsive force. So now this is 0 point, which there's no force to each other exerted, influencing to each other. So these are, if the distance of two atoms are far away, and of course there's no force acting onto each other. So there's no force in here. Now, as you learn in general physics, there is attractive force in a certain distance, and then this is maximum distance. Actually, they have force attracting to each other, and that there's some maximum, some optimal, I should say, optimal distance d. And then what happens? They closer to this critical distance. Then actually they provided the repulsive force. So these two atoms are close to each other because of the charge that provided the repulsive force to the infinite magnitude if they actually try to collide each other. So that will not happen. So this distance d is the maximum distance to attach each other. So this is maybe energetically stable situations in here. So why did I bring up this the general physics term? Is because to explain how the probe actually doesn't touch surfaces, the object and surfaces actually they can actually image. So if you can interested in about, say, you can think about this distance. Say now if you have very, very sharp tip that can be maybe, think about several atoms. several atoms here. And then there's some object, in this case maybe protein, comes here. It's a similar situation here. You have this distance are far away to each other. If this distance is far away, that's corresponding to this area. This is far away distance is corresponding to this area. That means there's no force acting onto each other. So there's no force that actually attracting this tip to the object. Also, the object doesn't have any force feeling from this object. But if you can imagine this probe is actually coming down. If there's a tool that actually bring this tip, several motors is connected to, and then bring it down, then in this graph there is this direction that can move. So now there is critical distance. Maybe they can start to have some attractive force, right? If they are close enough, but actually not touching to each other, because touching to each other has to be this area. This is actually contacting area. Then, in this distance start, this tip feeling some magnitude of force. Because of this general physics, right? Because it's the attractive force acting onto each other in a critical field of the distance. So this is how they start to actually develop the non-contact mode operations to here. So let's a little bit more detail, go into the detail then. So now think about this situation. Now this, what if I brought this object. So this object actually, if you can touch here, something like this, then they can vibrate it, right? This object is vibrating. But interestingly, even if you providing a large force to have a large amplitude like this, or you provide a small force like this, and providing like small amplitude of this vibration. The thing is, you can actually see that the frequency of these vibrations, right? Frequency of the vibration, no matter what the force is, right? That means the vibrations of each object. That can be the guitar string, or any object that you can feel or not feeling anything, but there's also always any object has a vibrations, a certain degree of vibrations. But of course, this one you can actually see the vibrations. The vibration frequency is fixed value, so you cannot change, because if you provided the object thicker or shorter of this, then now you can see the change of the frequency. Now this you cannot. Now this object you cannot change the thickness of this metal, or the length you cannot change. No matter what, you can provide a large force or small force, but you cannot actually change the frequency. This is what's called resonance frequency. So the resonance frequency is the value, fixed value you cannot change. It's depending on the physical properties, the physical dimensions of the object. Or I should say dimensional property, physical properties of an object. So if you can change, if you want to change the resonance frequency of an object, this physical properties dimension should be changed. Otherwise, you cannot actually change the resonance frequency. And similar, like when I mentioned the tip, but if the tip looks like this, they can actually vibrating, and then the tip is now at the end of this here, it looks like this, and this the end of the tip, and then you're now vibrating, right? And the tip is actually vibrate with this backbone, right? This is kind of situations where you have a fixed point, and then you have now this fixed point and this, so you can actually vibrating from here to here. This is maybe, I will say, the amplitude 0. So again, this amplitude 0, or the frequency, I will say frequency 0, cannot change unless you change these properties, physical properties of this cantilever dimensions. But anyway, so if you can fix this and then now start the vibrating here, so now we can vibrate this point, and then they actually start like this, vibrating continuously, because you can provide a force. Maybe I can show you this like this. Maybe situations like this. So the resonance energy provided to here, and now this continuously vibrating, and then they goes down. This point goes down to the object, right? So if this vibrating point, actually this the below the lowest point distance from the top point of the object is, in this situations here, now this distance actually going down from here to this area, then this probe now feel the force because of the general principles of the two atoms situations. So what happens now? Then when they go close to each other, then their amplitude, so new amplitude, which is A1, will be larger, because if you can vibrating like this way, and then they close to each other, the distance close to each other, they actually attractive force. So generally, if there's no attractive force of this amplitude, and there is amplitude that attractive force more, then actually go down a little bit more, and then actually amplitude it becomes higher, right? So then this A1, which is a new amplitude, should be larger than the A0. So that is the actually principle. This is the key principle, that actually how this probe actually doesn't touch the surface, but actually they know already close to each other from the object at the top surface, because of the distance is different. Then how we can imagine, how we can image the following this exact morphology of the surfaces. There is a question now. If they vibrating, then vibrating distance goes in here, then they vibrate in this level, and then they goes a little bit atom scale. You can think about the atom scale, a little bit closer than this A2, larger than A1, larger than A0. At the point here, so A0 point is this point. I should say A1 point is here, A2 point is here. But they close each other. The force is larger, attractive force is larger, then amplitude of vibrating object is larger. So it makes sense, right? So now the machine, say I want to have the continuous, like a feedback. There's a feedback loop that exhibit a fixed amplitude value such as A1. In other words, that I don't want to have A0 value. I don't want to have A2 value, I always want to have the A1 value. Now how we can achieve it, then if there's say if I will have only A1 value here, then the probe actually goes down, which is this direction. Then the amplitude becomes larger because of the attractive force. And then I don't want to have this A2 value direction. Then this vibrating point actually goes a little bit up to have this constant A1 value. In other words, that this is basically scanning probe microscopy. So the probe is actually vibrating at the same time they scan like each other. Situations you can vibrating here now. And then when they goes from here to here, then their distance from the surfaces and the probe is become closer and closer. So that means the direction is going from here to here. And the amplitude becomes larger and larger. So in that case, the system actually it detected that the amplitude becomes larger, then they think, oh, I have to go a little bit off or lift up this probe system. So a little bit up, a little bit, and then until it goes up, and then the amplitude will be decreased. But I don't want to have a too much decrease of the amplitude, so then it goes down. So they can vibrating. So this fixed point actually goes up and goes down, but they can actually see a constant amplitude like this when as they move this x directions. That is how they image of this following this contour imaginary surfaces of this object. Even if the tip does not touch the surfaces, only have this distance, for example, they fix only this distance 1 continuously. In this case, this can be distance 1, and have this same apology of this they can actually image. So this is how they operate. So then the question is how they detect it, how they measure such an amplitude change, because that is a key, right? If their amplitude becomes larger and larger as the probe goes from this direction to this direction, if there's no way, if there's no method to have such an amplitude change, then the whole system becomes useless. So then what they do is now they use the laser. They use a laser here. There's a laser providing here, so you can actually hit it on top of it, and the laser deflected, and there's a detector. I should draw a little bit more line. This is called the detector, but this is a special name, is a photodiode. Photodiode detector. This photodiode means this is photon, which is a light. Light in this case is a laser. That when you hit it here, then this diode providing the voltage. So they actually converted the photon energy to electric voltage energy. So this is a diode. You can see actually a lot of spectroscopy. So the most simple spectroscopy you learn in the undergraduate course is UV-vis, ultraviolet visible spectroscopy. This is actually, they use the photodiode because you have the light comes, the sample absorbent and the color, then the photodiode providing a different voltage, so that then they to see the absorption of the molecule. So the UV-vis spectroscopy has to have the photodiode here. Same, the AFM has photodiode detector, but they are position sensitive. So the difference is position sensitive. Position sensitive means when they hit it here, they provide voltage A, provided here, then the laser pointed here, they provide a different value of the voltage. So in this case, they vibrating. So then they deflect it to a different angle. So actually they're vibrating, and there's a laser. The heated air goes here, and then there's a line that comes up. As a result, the vibration resulted in the laser actually goes like a vibrating like this. Line situations, line result detecting on this position sensitive photodiode. So each position has a specific photodiode, so you can actually tell the machine that I was activated, I was activated, I was activated, I was activated, but not activated here. So they can actually see the length of the amplitude. So now everything makes sense, because this tip goes from far away to the close to each other's surfaces, and then the amplitude becomes larger because of the attractive force from the surfaces. And then this A0, if this is A0 amplitude, then the A1, A2 as goes to the closer, then they have a different amplitude and larger different amplitude. That is how they work. So how the feedback loop system controls that when this, say I want to have always this value, this close to each other too much, then go back by lifting up this motor system. If they far away too much, then they bring into the surfaces down. So this feedback loop is very fast, so then they can actually see the dynamic change of the height of the surfaces. They can actually see the morphology of the surfaces.